So now we continue with per unit system analysis. So how you define per unit value of an electrical quantity? You know, actual value by base value. So how do you write this one? It is actual value, or you say the absolute value. So the feature of the absolute system is included place. Absolute system of the electrical quantity expressed in units. And this whole divided by what? Base value or reference value. Of electrical quantity expressed in same units. Expressed in the same units. Now we check how to express per unit reactance in terms of base voltage and base current. Now in general we should say per unit impedance, but why you neglect resistance and find per unit reactance only for the sake of calculation convenience? And the error due to neglecting resistance is 3%. So in spite of 3% negligible error, for the sake of calculation, always we calculate percentage reactance. So now we check the second aspect, expressing per unit reactance in terms of base voltage and base current. Per unit reactance in terms of base voltage and base current. So for our analysis, you consider two machines, machine 1, machine 2, voltage ratings V1, V2, current ratings I1, I2. Then how you select base value? Selection of base value is optional. So you can select machine 1 ratings as base values or machine 2 ratings as base values. So what are the machine 2 ratings? V2. Take it as base voltage. Machine 2 current IB is I2. So now first we check how to write the per unit voltages. So V1 per unit, how to write? The actual value of V1 in volts by the base voltage also in volts. Base voltage is V2. How to write V2 per unit? Actual value of V2 in volts by the base voltage also in volts. VB is how much? V2 it is 1 per unit. Similarly, you can check the per unit currents. That is I1 per unit and I2 per unit. How to write I1 per unit? I1 measured in amperes by the base current in amperes. Actual value of I1 measured in amperes by the base current in amperes, I1 by I2. How to write I2 per unit? Actual value of I2 in amperes by the base current in amperes. So I2 by I2, how much here? 1 per unit. So these per unit voltages, per unit current. Similarly, how you find the per unit reactances? X1 per unit. How to write? Actual value of X1 in ohms by base reactance in ohms. And how to write X2 per unit? Actual value of X2 in ohms by the base reactance in ohms. And how to write what is the base reactance? Base reactance in ohms is the base voltage measured in volts divided by the base current measured in amperes. So in general, how to write X per unit? X1 per unit is X1 in ohms, X2 per unit X2 in ohms, X per unit is X measured in ohms. XB, how to write? The VB measured in volts divided with the IB measured in amperes. So what is X per unit? X in ohms multiplied with the base current in amperes multiplied with the base voltage in volts. So this is the formula to find out per unit reactance. But all the electrical machines do not have their ratings only in voltage and current. They are also rated in volt amperes and voltage, like transformers. You know, for transformers are rated in volt ampere and volt. So we have to express per unit reactance in terms of base volt ampere and base voltage. So next analysis is expressing per unit reactance in terms of base volt ampere and base voltage. So for that we consider the second equation. So what is X per unit? X in ohms, base current in amperes by the base voltage in volts. What you will do is you multiply in both numerator and denominator with VB by 10 power 6. So what is X per unit? X in ohms, base current into VB by 10 power 6. Here again VB by 10 power 6. So the reactance in ohms, VB IB by 10 power 6. Here VB by 10 cube whole square. Vb by 10 cube whole square. And what about Vb Ib by 10 power 6? It is the base MVA. What about Vb by 10 cube? It is base kV. So this is how you find what is the per unit reactance. So how to find the reactance in ohms multiplied with base MVA by base kV. Now which voltage? Phase voltage or line voltage? It is line to line voltage, please. Which MVA, single phase or three phase? It is of three phase. Now once you know this per unit reactance, how to find what is percentage reactance? Percentage reactance is 100 into per unit. So how to write per unit? First substitute this formula. X in ohms multiplied with the base current in amperes by the base voltage in volts, or 100 into, substitute this formula, X in ohms multiplied with the base MVA by base kV square. So this formula is important. Per unit reactance into 100, you get the percentage reactance. Now next one is how to express the base reactance in terms of base volt ampere and base voltage. For that you can refer this equation. So what is the base reactance in ohms? You want to express in base volt ampere and base voltage. You consider this voltage equation. Base reactance is the base voltage measured in volts by the base current in amperes. Now multiply both numerator and denominator with Vb by 10 power 6. So the base reactance in ohms is Vb into Vb by 10 power 6, Ib into Vb by 10 power 6. Simplifying, how much? Vb by 10 cube whole square. Here Vb Ib by 10 power 6. What is Vb by 10 cube? Base kV. What is Vb Ib by 10 power 6? It is base MVA. So this formula is regarding the base reactance in ohms. Now further we have to analyze. Suppose a power system network is further extended. Say initially there are 3 units each of 500 megawatts. You have some X per unit. Say further 2 more units are commissioned each of 500 megawatts. You won't have the same per unit reactance. Then how to express new per unit reactance in terms of old per unit reactance? So this is useful whenever you want to extend the existing power system network. So sixth one is new per unit reactance in terms of old per unit reactance. So how to write what is X per unit? Use that equation 3. The reactance in ohms multiplied with the base MVA by kV square. Say these are the new values. And previously you have some per unit reactance. So this you can express in terms of volt. Now divide these two now. Find what is new in terms of volt. Now you have the ratio of two different terms. So you will have the ratios of MVA. You will have the ratios of kV square. Important is where you write volt and where you write new. This MVA, where it is in the numerator. So start with N, you can write new. Start with N, you can write new. So if it is new, denominator volt. Here the reverse ratio is volt by new. So this is the new per unit reactance expressed in terms of volt per unit reactance. So these are important formulae. So in general, for our calculations, you come across frequently the equation 3 and this equation 6. And further, how you find the short circuit current? It is 100 by the percentage X into base current. In amperes you want, this base current is in amperes. Then how you find short circuit MVA? Same, 100 by percentage X into base MVA. So multiplied with what? The base MVA. Now next we come across the features of per unit system. The first one is the primary and secondary per unit reactances are equal. Primary and secondary per unit reactances are equal. Now you find out the base kV. So calculated, so the kV, the voltages, actual values calculated with respect to base values, whether they are line to neutral or line to line, it is same. Similarly, the ratios of MVA with respect to base MVA, MVA with respect to base MVA. So it is of single phase or three phase. Both are same. So these are the three features of per unit system analysis. And this you can make it as the equation 6, 7, 8, this total 9th one. So please go through all these formulae of per unit system analysis. So these are important for our analysis of per unit system. Now we solve the questions based on the per unit system. So we have to calculate what is the per unit impedance of a three-phase alternator rated 1000 kVA, 33 kV, having armature resistance and synchronous reactance 20 ohms per phase and 70 ohms per phase. So how you calculate the per unit impedance? You have to find what is per unit impedance. Per unit, how to write? The actual value of the impedance in ohms divided by the base impedance in ohms. So actually how much? 20 plus J70. How to find what is the base impedance? You know the formula, we have written base impedance in ohms. How to write? Base kV square by the base MVA. So how much kV? 33 square. 1000 kVA means 1 MVA. So how much you get? 1089 ohms. So divide with that 1089 the base impedance in ohms. You get 0.018 plus J 0.064 per unit. So this is the per unit impedance. Now next is a common data question. The ohmic value of the reactance of the winding of an alternator rated 500 MVA, 22 kV star connected winding having 1.1 per unit reactance is. So we have to find out the ohmic value of reactance per unit given 1.1. So you know this formula per unit, how to write? The reactance in ohms multiplied with base MVA by base kV square. And now you substitute the values. X is 1.1, reactance in ohms you don't know, base MVA 500, base kV 22 square. You simplify this and find out the reactance in ohms. So 1.0648 is the reactance in ohms. Now the continuation question is, the per unit value of reactance of alternator winding on specified basis (100 MVA, 20 kV) is. So you know this formula. X per unit nu is X per unit volt multiplied with nu base MVA divided with volt base MVA, all divided with kV square volt by kV square nu. So previously per unit how much? 1.1. New values are 120. Old values are 522. How much you get? 0.2662 per unit. 0.2662 per unit. Next question is, base kV and base MVA of a three-phase transmission line is 33 kV, 10 MVA. So the base current and base impedance are. So how to calculate the base current? You know base volt ampere is √3 times base voltage base current, 10 MVA, base voltage 33 kV. So find out what is base current. 174.9 this value. And how you find the base impedance now in ohms? It is base kV square by the base MVA. How much base kV? 33 square. Base MV is 10. So how much you get? 108.9 ohms. So you get the answer 108.9 ohms. Now we solve this next question. A 2 kVA, 250 by 25 volts single phase transformer has equivalent impedance of 2.6 plus J 4.3 ohms when referred to HV side. Now the question is, what will be ZEH when referred to HV side? Are given in so we calculate what is the ZEH with respect to high voltage side. So how to calculate this one? You want to find the answer in ZEH referred to high voltage side now in per unit. In ohms is given. How to find in per unit? You divide with the base value. So what is the base impedance in ohms? Formula is kV square by base MVA. How much kV? High voltage side 250 volts. kV means divide with 1000. How much MVA? 2 kVA. MVA means you divide with 1000. How much you get on simplifying? 31.25 ohms. So what about ZEH per unit now? The actual value 2.6 plus J 4.3. Base how much? 31.25. As the options are in polar form, you convert these values into polar form now. You check the magnitude. in all the options the magnitudes are different. Okay, no need to check the angle. Check the magnitudes and simplify. You can get the answer. 0.161, angle is 58.8 per unit. A three-phase transformer rated 20 MVA, 220 kV star, 33 kV delta, has leakage reactance of 12%. The transformer reactance in ohms referred to each phase of low voltage delta connected side is. So you want to find the reactance in ohms. So what is the percentage reactance? 100 into per unit. Are you right? The reactance in ohms multiplied with base MVA by base kV square. 100, how much reactance? 12. Now, reactance in ohms we have to find out. How much base MVA? 20. How much kV now? Delta connected side is 33. So find out the reactance in ohms. You get the answer 6.53 ohms. So on simplifying, you get the answer as 6.53 ohms. And now we solve this next one. This is asked in one of the IAS question papers. Three generators rated 100 MVA, 11 kV have an impedance of 0.15 per unit each. If in the same plant these generators are replaced by a single equivalent generator and the effective impedance of equivalent generator is. So you are having three generators in parallel. So how you represent them? With the reactance and source in a series. Point 0.15, 0.15, 0.15. So what will be the equivalent reactance? 3 times 0.15 are in parallel. So what is the answer you get now? 0.05 per unit. 0.05 per unit. So this is how you find out these calculations. Now we check and analyze why you require symmetrical components in a power system network. So why you require and what is the significance of symmetrical components in power system network? You require symmetrical components to analyze an unbalanced system. Most important point, why you require symmetrical components to analyze an unbalanced system? To analyze an unbalanced system. Now to continue with the analysis, you consider this alternator connected to the load. For this, you should draw the per unit reactance diagram. How to draw this one? You connect the reactance and alternator in series and say the reactance is X per unit, alternator EMF generated EG per unit, say the current delivered by the alternator is I per unit and flowing through the load. And at load what you will calculate? Terminal voltage Vt per unit. where you calculate always between the phase and a neutral. Always between phase and a neutral. So what about the terminal voltage Vt per unit out of the EMF generated? Subtract the reactive drop Ji per unit into X per unit. So name it as the equation 1. Now previously in the analysis of per unit system, we said that number of equations required to analyze performance of power system network is equal to 1, irrespective of number of voltage levels. And this equation 1 is that one equation representing the per unit system analysis. So I repeat, in per unit system, we say that number of equations required to analyze performance of power system network equal to 1, irrespective of number of voltage levels. And this is that equation Vt per unit is Eg per unit minus J I per unit X per unit. So how you draw the per unit reactance diagram? It is drawn with the reactances of the power system components with terminal voltage measured between phase and neutral. Terminal voltage measured between phase and neutral. So this case 1, say you refer to a balanced load. Now we refer case 2, unbalanced load. So if it is unbalanced load, what is the change? You have to find terminal voltages separately for R phase, Y phase, B phase. That means we should find out VTR per unit, VTY per unit and VTB per unit separately. How to write this one? EGR per unit minus J IR XR per unit. Indicate the subscript R here for R phase. Similarly, we complete for Y phase. And similarly, it is for B phase. This is for case 2. Now verify to the right side of this equation set 2. How many unknown quantities do you have? Total 9 unknown quantities. How many you are having? Total 9 unknown quantities. So how to find out these 9 unknown quantities? For that, we have to develop 9 symmetrical components. We have to develop 9 symmetrical components. So number of unknown quantities is equal to 9. And therefore number of symmetrical components also 9. So evaluating 9 symmetrical components is time consuming. So check how to minimize the symmetrical components For that, you should know about operator K, or you say A or alpha. So for that you require operator K or A or alpha. What is the purpose of operator K? Operator K rotates a vector in anti-clockwise direction by 120 degrees. Operator K rotates a vector in anti-clockwise direction by 120 degrees. That is the function of operator K. Rotates a vector in anti-clockwise direction by 120 degrees. Say the voltage is V. Apply operator K, rotates V in anti-clockwise by 120 degrees. So by the time you get the vector, it is kV. Again apply the operator K, it rotates kV in anti-clockwise direction by 120. By the time you get K square V. Again you apply operator K, it rotates in anti-clockwise direction by 120. So by the time you get K cube into V. So these are one and the same. If V is same as K cube V, what we conclude? K cube is 1, or you say K is 1. But in the polar form, how to write what is the value of K? Magnitude is 1, angle is 120. Plus 120 or minus 120? It is in anti-clockwise directions, assigned positive sign. Why positive? Because it is in anti-clockwise direction. That is, in the rectangular form, minus 0.5 plus j 0.866. And how to write what is K square? K into K. 1 at angle 120, 1 at angle 120. How much 1 at angle? 240. So minus 0.5 minus j 0.866. Add that K and K square, it is minus 1. So how much you get? 1 plus K square, 0. How much you get? 1 plus K square, 0. So these relations are important here. It rotates a vector in anti-clockwise direction by 120. And what about this 1 plus K square? Its value is 0. And the values of K in polar, rectangular, and K square also in both polar and rectangular. So using this operator K, we check after the break how to minimize 9 symmetrical components to 3 symmetrical components. Now you have 5 minutes break.